A very important force that we're going to take a look at, that we'll actually take a look at in much more detail later on, is the force from a spring. Let's imagine that we have a spring and we put a mass on it. That mass stretches the spring like this. Now, there are several things going on. I'm exerting a force on the spring up here with my left hand. The weight of the mass is due to the attraction of the earth, is applying a force to the bottom part of the spring, and that force is then stretching the spring a certain amount. We're going to make this a little bit easier to deal with, rather than having my hand holding it here and gravity pulling down on the mass here. We're going to take this whole thing and we're going to turn it sideways, and let's just imagine that we can rest this on a flat surface, like a table or something. So we're going to look at this sideways. That will allow us to ignore the weight of the object, because the weight of the object will be acting vertically and not in the direction of the spring. So what we end up with is something that looks like this. So here we are going to assume that one end of the spring is fixed to a wall, it's attached to a wall, so this is not moving. This end here, not moving. Then the spring comes over here and is attached to our mass, and we'll assume that the mass is resting on some frictionless surface. So as we move the mass back and forth and there is a force exerted on it by the spring, we will not have to worry about friction at the moment. We'll take a look at what happens when there is friction later on. When we have this set up, we notice that there is some rest length for the spring. So when there's no force acting on it, the spring has some certain length. We'll mark that position of the spring, or what I'll say is we'll mark the position of where the mass is. You can mark the front end or the middle or the back or wherever, however you want to mark it. We'll mark this as our origin, so that x, which we'll use for the position of our mass, is equal to 0 at equilibrium. Whoops, I spelled that pretty badly. Equilibrium. There we go. So when the mass is at a point where the spring exerts no force on the mass, we'll call that the equilibrium position. Now what happens? Well, if we take the mass and we stretch the spring by moving the mass to the right, what happens? Well, the spring pulls back. Okay, the spring pulls back on the mass to the left. So let's move our mass, say some position over here to some position x. What happens? There is a force pulling on the mass back. Where? Back towards the equilibrium position. Also, this spring doesn't have much space, so to speak, but you can imagine if you compress the spring then pushes back to open it back up. So when you compress the spring this way, so imagine moving the mass back this way, the spring actually pushes back to the right. Well, this is interesting. If the displacement of the mass is to the right, in other words, in a positive direction, the force is to the left, in a negative direction. If the compression or the displacement is to the left, in the negative direction, the force is back to the right. We call this a restoring force, because the force of the spring is always trying to restore the mass back to the equilibrium position. What we have then is that the force, and we'll write this, well, I won't write this as an equal sign. We'll say that the force is somehow related to the negative of the displacement. The bigger the displacement, the more force we get. A little displacement gives us a little force. The big displacement gives us a much bigger force. So, as x increases, the force increases. and they're in opposite directions. So we'll put a minus sign in here. We could make this a vector equation if we wanted to, but we'll just leave it in terms of the position of the position x and the force. And we'll just keep in mind that a positive x is displacement to the right, or stretching, negative x, compression, displacement to the left. And then the force, positive force means a force to the right, negative force, force to the left. So we have a minus sign in here to indicate that these two are in opposite directions, but not necessarily proportional to each other or what the relationship is. A real spring will have a very complicated relationship between the force and the displacement. Obviously, in this case, we can't compress it very much until all the coils are all on top of each other, and then it would be very difficult to compress it. Likewise, if we stretch it too much, eventually all the coils will stretch out and we'll just have a piece of wire, which would be very, very hard to extend any further than that. So there is a complicated relationship between the force and the displacement. But if we define what we'll call an ideal spring, an ideal spring is one where the force is actually directly proportional to the displacement. What we can do then is actually turn this into an equality and put in a constant of proportionality, K. K is called the spring constant. And it tells us basically how strong the spring is. Do we have a spring where it's very difficult to stretch it even a little bit? If a little stretch gives us a big force, that means we'd have a big value of K. Little x, big K still gives us a big force. If we have a small value of K, that means that it would take a very large displacement to give us a large force. So a small value of K means we can stretch it very easily without much force being applied. So the spring constant basically tells us how strong the spring is. Small k means a weak spring. Large K means a strong spring. Okay, very, very good. And the units of K, we could just see dividing by x, the units of K will be the units of F divided by the units of x. Excuse me. So the units of K will be newtons per meter. Those will be the standard SI units. Okay, great. So that's one force that we might see in some kind of situation. What about some others? Sorry, forgot to mention one more thing. This relationship, F equals minus kx, which describes the relationship between the force and the displacement for an ideal spring, this relationship is called Hooke's law. That is named after Robert Hooke, who was a contemporary of Sir Isaac Newton, who was also looking at forces and things like that when Isaac Newton was working. Okay, so F equals minus kx, Hooke's law. We'll see more of that later on. The normal force is a force we've already talked a little bit about, but I'd like to just go over it again. Starting with Newton's second law, F equals ma. We can use this in two very broad ways. Typically, we'll use it in two very broad ways. One is going from F to ma. The other is going from ma to F. What do I mean by that? If we know the forces acting on a mass, we can add those together and use this result to figure out what the acceleration of the mass is. On the other hand, if we know what the acceleration of the mass is, we can work this way and figure out what the net force acting on an object has to be. Let's do that in this case. Let's imagine we've got some mass, and let's assume for this case that we know what the mass is, whatever m happens to be. If it is just sitting on a table, not moving, what's its acceleration? The acceleration is 0. If the velocity is not changing, the acceleration is 0. In that case, we know a is 0. But if a is 0, that tells us that F net has to be 0. So if a is 0, that tells us that F has to be 0 in this equation. And remember, what is that force in F equals ma? It's the net force. It's the total force. The total force acting on the object. That means that the vector sum of whatever forces are acting on M have to equal 0. But we know that there is at least the weight of an object acting, the weight of the object acting on the object. So what's the weight? Well, we know that's going to be a force that acts straight down, the attraction due to the Earth towards the Earth, and the weight, remember, we said has a magnitude of m times g. Well, if there are no sideways forces, if there are no forces acting horizontally, we might say in the x direction, and there is a weight acting on the object, well, we know the net force in the y direction has to be 0. So if we've got one force acting down, we must have another force acting up. And where is that coming from? It's coming from the table. You might think of this in terms of if I were to release this mass, we know it's going to fall downward because there is a gravitational force acting on it. The weight. What is the magnitude of the weight? Well, we know the object accelerates at g because F equals ma. If it's accelerating at g, a is g, so we have mg. The force must be equal to mg. So the force of gravity acting on the object is mg. But now if I hold it in my hand, I am applying a force on it upwards that is balancing that weight downward. And that's what you experience as the weight of an object. When you hold something, what you're doing is you're feeling that you're balancing that force, the gravitational force. You are applying an opposite force, opposite gravity, balancing that gravitational attraction downward. So if the object is sitting on a table, where is that force coming from? It's coming from the table, and it's acting upwards. And that is what we call F sub capital N. I'll try and distinguish between these. I'll use a capital N for the normal force, while a little n is for the net force. So that tells us that we have a normal force acting in the opposite direction as the weight. In this case, in general, it's going to be always perpendicular to the surface. So remember, normal and mathematically means perpendicular. And so in this case, this force is perpendicular to the surface that the object is resting on. We'll see later on that if we were to incline the surface, that the normal force would still remain perpendicular to the surface. And we must have other forces then acting along the surface. We'll see that later on, shortly. But let's keep in mind, normal force always perpendicular to the surface, and as we talked about earlier, it will vary its magnitude to balance whatever it needs to balance to keep the object stationary, to keep the object from burrowing down into the surface, so to speak, or from flying up off the surface. Okay, great. What other forces can we take a look at?